Now let's talk about the pros and cons of CUR. One of the advantages of CUR is easy interpretation. Since the basis vectors are actual columns and rows in the input matrix A, this means we can interpret the concepts using actual users or movies. Let's say that we have a bunch of points on the left here, and we want to perform dimensionality reduction. And SVD will just project these points on this singular vector, which is optimal. In contrast, CUR will project this point on this actual column, which is actual data points. And this is still a very good approximation, as you can see here. The second advantage of CUR is the sparse basis. Since the basis vectors are actual columns and rows from the sparse input matrix A. And one of the disadvantages of CUR is that there might be duplicate columns and rows. And this is because the columns of large nodes will be sampled many times. But this issue is easy to solve actually. Specifically, if we want to get rid of the duplicates, we can just throw the duplicates away and we can keep only one copy. And then we can scale or multiply this only one copy of columns and rows by the square root of the times of these duplicates. So basically, after doing this, we can get a smaller intersection of this C matrix and R matrix, and therefore construct a smaller matrix U. And comparing CUR and SVD, we can see that both of their input matrices, they are both huge but sparse. But in SVD, the matrix U and V, they're actually very big and dense, and therefore they will take up a lot of space to store. But in CUR, the C matrix and R matrix, although they're also very big, they're actually very sparse, and therefore it will take up much, much less space to store. And for SVD, the middle matrix sigma here is sparse and small. And in CUR, this U matrix, it's dense but small. But since both of these matrices are very small, whether or not they are sparse or dense, it doesn't really matter. So to summarize, CUR actually needs much, much less space to store the results, basically to store these three matrices, C, U, and R. And to see the difference better, let's do a simple experiment on the DBLP dataset. And DBLP is just a bibliographic dataset where we have a very large and sparse matrix, and this matrix is a author to conference matrix. Basically, the entry A sub ij will just be the number of papers published by author I at conference J. For example, here we have a matrix and this is the ith row. Then the entry A sub ij will be just the number of papers that this author published at conference J. And in this data set, we have about 428K authors or rows, and we have around 3,000 conferences or columns. And note that this is actually a very sparse matrix because one author usually they only publish in a very, very small number of conferences, like 5 or 10. And if we want to reduce the dimensionality of this matrix, we ask the questions, how much time does it take? And what's the reconstruction error? And how much space do we need? And here's the result. And we can see that these blue triangles represent the result of SVD, and the red circles represent the result for CUR, and the black rectangles or black boxes represent the results for CUR with no duplicates. And the horizontal axis is the accuracy, and accuracy is actually 1 minus the relative sum square errors. So basically, the larger the accuracy is, the smaller the reconstruction error. And the vertical axis is the space threshold. So the higher it is, the more space you're going to need. And we can see that for the same accuracy, SVD actually takes up much more space. And similarly, if we look at here, for the same accuracy, SVD needs much more time to compute.